And it works. Okay. Hello, everyone. Thanks for the intro, Jack. Today, I'm going to be talking to you about digital humans. You know, we're at a symposium for digital humans, but I'll be talking about it from a slightly different angle. Partly because I'm in industry, so I'm in Microsoft, but also partly from the use case of digital humans. So when most of us imagine digital humans, we imagine them as for human consumption. We're thinking of things like photorealistic avatars. So we have an offering from Azure on that. There's companies like Synthesia working on this, and the end goal is for human to consume that information, to sort of watch that digital human. We have stylized avatar representations that you can appear as an avatar in Teams calls, or any other remote collaboration app. There's just so many of them, and again, that's intended for human consumption because you sort of represent yourself as an avatar and for consumption by other people. And we have maybe something in the middle of realism stylization spectrum. We have digital humans for video games or film, and one example of that is MetaHuman from Unreal. So one sort of shared thread between those is who's intended audience of it. What I'm going to talk about is how we can use technology of digital humans to empower various computer vision applications, from motion capture to tracking to segmentation or normal prediction, or anything really you can imagine that you want to do for human understanding. You can really power using digital human technologies. So let's kick off. So the typical components of a digital human pipeline, and again, not every pipeline has the same components, but just sort of slight generalization. We have geometry models. We typically have a way to model statistically what the shape of a person would be, whether that's anatomically correct, stylized, somewhere in between. We have ways of modeling the appearance and rendering that imagery. So we don't just care about geometry. We want to dress those people, put them in particular environments, render them either real time or offline for creating imagery to be looked at. And then often we have part of technology that involves tracking the faces or bodies. Especially if you want a live interaction, if you want your avatar if you want to drive your avatar live in a Teams call, you need to have tracking technologies. And what I'll be talking about is how we can use these digital human technologies for computer vision, and how they actually combining them and using the same sort of pipeline for them really brings a lot of the magic, because they sort of lift each other up. And this is what, in our team at least, we call the virtuous cycle. So if we have better parametric models or geometry models of humans, we can build much better appearance models. We can sort of create much better imagery, which will lead to better tracking. That will in turn lead to better parametric models. And hopefully you'll sort of get what I mean by the end of the talk. And I think sort of one magic that comes from it, if you use the same parametric model in all parts of the pipeline, you can build much, much better technology overall. And so, often, to anyone who's worked on this, sometimes you have, you're tracking with Flame, but you're rendering with something else. There's translation, there's clashes, and you just sort of lose fidelity very quickly. And I'm going to talk a bit about that. So let's start with the parametric models. And I'm going to be talking about the tools we have internally in Microsoft, but there's a lot of similar tools and similar methodologies out there. So apologies if I miss citing people, but this is specifically just from Microsoft perspective. So first, what do I mean by a parametric model? Or sometimes people call them 3D morphable models. There's neural models for these things, but sort of at a basic level, I'm talking about having some sort of geometry template that we start with, adding identity or sort of morphology, sort of who you are to that template, then adding expression and pose. And sometimes expression and pose are the same thing. In our case, we separated because one's controlled by blend shapes, the other's by bone rig, but slight detail that's maybe not that important. So what we have built in Microsoft is a parametric face model to capture sort of how face shape varies across human population. So we're really interested in capturing as diverse representation as possible. We built it from about 1,000 scans that were retopologized to the same template. So and by that I mean, the tip of the nose in one scan is going to be the same vertex, tip of the nose in another scan. And I'll get in a moment to why that's really difficult, because turns out almost no part of the human face is rigid or consistent across different people. You sort of need to create these definitions. There's even when you start thinking, oh yeah, tip of the nose, that's easy. Every person has a tip of the nose. I'll give you 100 images of people and sort of ask you to pinpoint that. That's just going to be so difficult. And whether I ask you in the morning, afternoon, or the evening, you're probably going to give a slightly different answer. So that's a sort of big challenge there. And we also, so in addition to identity, we also have an expression basis, which is sort of this linear blend shape basis created by an artist. So I mentioned, so we have about 1,000 scans of people. Actually, rather than acquired in-house, there's a lot of companies that do that. There's companies for video game productions, for movie productions that will just sell you scans of people. We also have a big expression library of expressions. So this is captured in-house with a multi-camera rig where we just sit a person in the rig and say, just make some expressions or follow a particular script, and then we capture it with multiple cameras and then register that data. And I'll go more towards the end of the talk of how we do that. But we have sort of really sort of large and diverse collection of expressions. Now, so how do we train this parametric model? And already mentioned it briefly, is we start from a scan of a person and then register it to common topology. And this is somewhat semi-automatic process, and we do it for about 1,000 scans and then train something akin to PCA, not exactly, but close enough approximation. Now, the challenge is, how do you register all of the data? What's consistent? What's the corner of an eye? What's the tip of the nose? And those sort of, maybe there's some consistency, but when you start diving deeper, it becomes really challenging. So one example that I wanted to talk about is eyes. And sort of eyes are really important for how we perceive each other, both from identity, sort of who we are, there's a lot of subtlety there, and from expression. So we want to model eyes well. And looking at this sort of reasonably small sample of people, you can see huge variation in the eye shape, in the eyelid shape, in seeing the eyelid crease. Some people have it, some people don't. It changes as we age. And coming up with a consistent definition is really challenging. So that sort of looking at a bit more deeply. So some people have the eyelid crease that's reasonably visible, but it might be sort of sunken in. Some people have an eyelid crease sort of on top of the eyeball. Some people might have, for one of the eyes, the eyelid crease might be there. It might, for another, it might not be. Once you blink, which I didn't realize before, an eyelid crease might appear or disappear. It's not something that stays statically there. It just is more of a dynamic property, even though we treat it as just something as part of viewer appearance. But for us, in order for us to build good parametric models, we need to know what is a consistent definition. Often people will ignore it and just sort of, yeah, looks fine enough. And for some use cases, maybe that's good enough. So here's sort of some more examples of what we mean by an eyelid crease. If this video plays, yeah. So this is a slowed down version. So in all of these examples, we don't see an eyelid crease, but when a person blinks, you can see it actually appearing. So it's hiding. It's hiding in your eyelid. Sort of once it rolls up in your eyes, the eyelid crease is there. So with that sort of insight, we decided, okay, well, let's start with that. Sort of like everyone has an eyelid crease. For some people, it's visible. For others, it's not. So let's annotate just the boundary of the eyelid of the eyelid crease. And I'm not going to go into sort of huge amount of detail how we accomplished that. We had an internal tool for annotating this and refining the annotation. But I'm just more illustrating the example that if you want to create really high fidelity parametric models of humans, you start needing to go into those details in order to be able to have a consistent definition of human anatomy. And maybe it's not going to be a perfect definition because, as I said, there's just really there's a huge amount of similarity across people, but there's almost never an exact point that you can find on every human in the world that's going to be the same. And we came with some of sort of in-house definition of what we mean by eyelids and the eyelid creases, defining hooded, partially hooded, non-hooded eyelids, and hooded eyelids with epicanthal fold. That meaning that the crease sort of is hiding inside the eyelid. And what we did then is sort of retrained our parametric model of the face. So this is the ground truth mesh sort of rendered. This is what we've sort of, without a consistent definition of an eyelid crease, if we train a PCA model, what we had before for our parametric model, and then if we have a consistent definition of an eyelid. So you sort of start getting much sharper features. And the reason we needed to do that is so that there's a product in Microsoft Teams. If you can represent yourself as an avatar in Microsoft Teams. And typically, if you want to represent yourself as an avatar, you'll go in. There's going to be, to those who play video games, a very video gamey character creator menu where you have millions of sliders and try finding your eye shape, your face shape, your lip shape. That's very laborious. It takes ages and it's difficult to actually make something that looks like you. So we have a feature where you can enroll yourself from a single photo that will create an avatar of you. And for your avatar to have your likeness, capturing your eyes is really important. And that's why sort of we did a lot of this work to sort of be able to model and capture eyes. So that concludes the bit about parametric face models, but let's move on to body models. So what we actually use is our in-house face model attached to SMPL or simple body models. So I expect most of you are aware what SMPL is, but to those who are not, it's, I would almost claim it as academia and industry standard body model that most people will use. It's a parametric model of both identity and pose with some pose-specific blend shapes. And in addition, there's an extension to SMPL, which has more detailed hands and feet, but we just sort of take an SMPL X model and sort of we just attach our face onto it because I believe our head model's a bit higher fidelity than the flame model for the face. Now, so talked about parametric models. So and already alluded to one of the use case for them. The other use case that's really important for us is if we have a really good parametric model of the human head, we can start generating really good synthetic data for training vision models, and I'll go into that in greater detail in the next section. But also we can use that to power our tracking methodology. So if we want to do monocular face or body tracking, multi-view face or body tracking, we have to have something to track. What is it that we're trying to track? And that's where our parametric models come in. And as already alluded, if you have the same model to generate synthetic data that you're going to be using for training various machine vision models and the same model for tracking, you can sort of plug it in all very nicely together. Right, so jumping to the next section. So now I'll be talking about synthetic data. And our teams, and as Jack mentioned, sort of our team spent a lot of time working on synthetic data. We have a long history of it, so I don't know if, to those who are familiar with the Kinect sensor, so a lot of that body tracking technology has been trained on synthetic data in our team. way before I joined, but HoloLens hand tracking technology also trained on synthetic data. And then we thought, oh, can we actually do the same for face tracking technologies? And, turns out we can. So here's an example of our synthetic face pipeline. And, these look like video game character-y. They look very visual effectsy. And I don't know, if you walk 10 meters back and squint, maybe you can be tricked that they're real people, but they're not. Turns out, for training a DNN, doesn't matter. It's fine. You can train models very successfully with data like this. And one thing that's great about synthetic data is that we have perfect annotations, consistent annotations across frames, across views. We can annotate things like each individual hair strand. We can have really rich annotations like normal maps or depth maps that would be really, really difficult to capture otherwise. You might require specialist equipment, and even that specialist equipment has noise. So, for example, for depth map capture, you could use something like LiDARs or Kinects, but there's going to be noise in that. You're never going to get perfect annotations. In addition to faces, we also have a pipeline like this for full bodies, and you can actually see how it sort of gets assembled. We sort of get identity, shape, pose of a person, then clothing, hair, accessories, and then we can place them in environments to provide sort of diversity. So, why do we want synthetic data? Well, partly because, you can create really good ground truth annotations with it and fairly realistic imagery. And we want to do that because data collection and annotation is hard. To anyone who's spent the time I don't know if everyone shares that experience, but for my PhD, a third of it is data. Wrangling data, collecting it, annotating, especially if you're not starting with an established problem in a data set that's already there. Data collection's hard, especially if you want to collect diverse populations, if you want to have people in diverse scenarios or use diverse sensors, so that everything sort of becomes this Cartesian product, exploding thing of, I need to cover all the bases. Annotating is also really challenging. I've already talked about it, but humans are inconsistent about annotations. You ask the same person on the same image, morning and evening, they'll give you a different answer. And that inconsistency often really tanks your model performance, because the model doesn't know what the answer is if you don't know, and it's probably just going to guess something in the middle. Some things humans just can't annotate. Things like, already mentioned, depth maps or normal maps. There's just no way a human can annotate that sort of information. And, and it can be very expensive to do annotations, because then you need to QA everything and re-annotate often, and it wouldn't be amazing if we had a system that just fell out of it for free. And synthetic data sort of is part of the answer, how you can do that. And one thing before I go a bit further is, by synthetic data, I mean, in this talk, I mean computer graphics-based data, so visual effects-based data. There's a lot of other ways of generating synthetic imagery, like diffusion models, now Gaussian splats that are very popular. There's previously we had GAN models. An issue with those models, even though they will create something that's visually stunning, and now we've got to the point where actually you can't tell apart whether this is generated or real imagery, it will not have the annotations. There will be some parts where you can maybe get certain type of annotation from a certain model. It might be a bit noisy, but if, say, you decided, oh, actually I want head pose. Actually, no, I don't know how to do that with a diffusion model. Or I want landmarks for, I don't know, like the outline of the eye or the eyelid. No, that's whereas if you build it up from graphics pipeline, you can get all of that. You can instrument all of that, even though the realism of the imagery itself is probably going to be slightly poorer. And it's a bit of a trade-offs and controllability of it. Another sort of big benefit of using synthetic data, at least in our team, and I've already talked about the quality of annotation, is the iteration speed. So you come up with an idea, oh, I want to be able to, I don't know, track. So actually, yeah, so one example was we thought of, for hand tracking in HoloLens, rather than just predicting landmarks on the fingers, we wanted, oh, let's predict a virtual landmark somewhere above the hand. So it helps us with disambiguating rotation. Because surprisingly, for a lot of models, detecting whether the palm's up or backwards, it's surprisingly difficult. But we sort of like, oh, let's add this sort of extra landmark. If you ask the human to do that, it would be a real struggle to annotate and think about how you annotate that data. You need to re-annotate everything. With synthetic data, oh, let's just try it. Oh, it worked. Or maybe sometimes, oh, it doesn't work. But you can iterate fast. You don't need to sort of, okay, now let's spend 3 months collecting and annotating data to test out an idea. All right, so I talked about the benefits of synthetic data and showed you some visuals. How do we build a face? Already talked about the geometry model. So I won't go into too much more detail about that, but just suffice to say that we take a random identity, add a random expression, independently distributed. Then we start putting textures, accessories, clothing, and environment. And I'll go into a bit more detail about those parts. So texture. We just use we sometimes call it exemplar-based model because, well, it's a model where you just pick one of the 1,000 textures we have in our library. We tried building diffusion-based models or GAN-based models to generate these textures. Just picking a random texture is as good, and you don't need to worry about like the complex systems of building those models. One thing about our textures, we had artists actually shave the eyebrows and facial hair if people had it, or if you often scan people, they will be wearing this wig cap, as you can see here. You don't want that in your texture. You want to put hair on top of it, or you want to add accessories on top of it. So you need to remove that. So there's a bit of work and imagination from artists to sort of like virtually shave them. I think in some Hollywood productions they actually have the actors just shave for these captures, but we didn't go sort of that route. Then we can sort of build. We have our albedo textures. We have displacement maps that we construct based from. If we fit our parametric model to a face, it's not going to capture all the subtle details. We capture that in displacement map. We also have this sort of like fine level displacement map, which is to capture pore level detail that we work out from albedo, because if something in your albedo image is dark, it's likely that it's sort of inset and there's some self-shadowing happening. So it's a bit of a hack, but actually creates visually nice imagery. And in addition to just putting a texture on a neutral head, we also have modulation of the texture based on your expression. Because if I raise my eyebrows, you'll see some wrinkling on the forehead. If I furrow my brow, there's going to be different type of wrinkling. So we built this system of tension maps. So if part of a face is tensed up, trigger slightly different textures and do it in a data-driven way, because we have in some scan data of ours, we have the same person making different expressions, and we can build these sort of texture maps. So once we put a texture on a person, it's time to put some accessories on them. And we have a big library. I think this is reasonably out of date. We have now 500 head hair grooms. So we commissioned a visual effects company in Cambridge to create head grooms for us. And this was a really interesting challenge. You want to create 500 head grooms, because you can't really buy that data from anywhere. There's no library of these things, and we wanted to have like actual strand-based hair, so we can create really rich ground truth annotations from it. And then, what do you create? What's a diverse representation of human hair? Human hair is infinitely diverse, and every year we get new hairstyles, and trying to cover reasonable amount of diversity in head hair and facial hair and eyebrows was an interesting challenge, and spending a lot of time on websites of hairdressers and stylists and trying to categorize. So we have a paper out which tries categorizing human hair into a taxonomy, because there's really no such thing. So if anyone is interested, I'll mention that paper a bit later on. But we have a Hermione paper in SIGGRAPH Asia on trying to capture, even describe the diversity of human hair. Just having the language is challenging. Then, once we add hair, then we need to put clothing on people. We have a digital wardrobe that we call, where, again, it's sort of a similar problem. How do you capture diverse enough appearance of clothing? And they're all just artist-created meshes with a procedural texture. So every time you see, the same, say you see a helmet, it's always subtly different. There's going to be slightly different reflectance properties, different pattern, and you can just build these sort of quite complex procedural shader graphs to for example, for a t-shirt, you can have different size of stripes and different hues of colors. We also have a collection of eyeglasses that you can also proceduralize quite easily by reflectance properties of the glass. You can also rig them on the face so that they move. If your face shape is different, that they'll adapt to that and to the face size as well. And one interesting problem with glasses, and maybe a slight tangent, is when you're building this pipeline, you also have to think, okay, how am I going to use it? What sort of ground truth annotations do I want from it? And glass is an interesting one because glass is a refractive surface. So if you want to, and when you're asking humans to annotate that, you just ignore it. They just ignore the image itself. When you're doing it through a rendering pipeline, now you start having to think, okay, if I want to annotate a landmark of a person's face, should I annotate the 3D sort of X-ray through the glasses, or should I annotate what the glasses refract? Because visually that looks a bit different. And then you start thinking, okay, but probably depends on how am I going to use it or how difficult that problem is to solve. So we ended up going for, actually, let's have our glasses not refract light. They'll have some reflections, but there's not going to be any refraction, so we don't have this inconsistency between what's annotated and what's seen in the image. But it's sort of great. I think you're in a great place when you start thinking about what exactly is my ground truth annotation, rather than what's capable, what can humans label reasonably consistently. So I already sort of alluded to this a bit about our procedural materials in our digital wardrobe. So you can see we have, say, the same geometry of a vest, but very different colors, and that sort of comes out for free, that extra diversity. And visually they look very different, even though it's exactly the same mesh. And we have the same for different clothing items. And that's why your likelihood of seeing the exact same item of clothing is quite small, even though we only have like 40 items. Here's a visualization of diversity of the type of digital wardrobe we have. And you can see a lot of face masks. That's a hangover from COVID, when we sort of needed to do some face tracking of people wearing face masks. Okay, and I'll let it run for a bit. All right. So, and now, we got the person fully dressed. Oh, and maybe a slight aside. So far, I've just been showing our face pipeline. We have something very similar for full bodies. The clothing's handled slightly differently, but it's mostly the same idea. So now when we have a digital human fully assembled, it's time to put them in an environment. And for your synthetic data generation, an environment's really important because it adds so much extra diversity to the imagery at a really low cost. So this is the same identity of a person, but put in an HDRI image. So it's just a way to illuminate the scene using high dynamic range imagery used in visual effects quite a lot. And I really like the image on the right there. So again, same identity, just in different lighting. And it looks drastically different. And that's great for training any neural network to do anything with faces, because you just get that diversity out of it. one other thing that's great with synthetic data is that it can, let me play the video, is that it can act as a data multiplier. So we say we capture a new expression sequence, just a single expression sequence. We can replay that same sequence on huge number of different digital humans. And it sort of has this Cartesian product effect where sort of adding an extra item of clothing, an extra hair groom, it sort of maximizes that diversity. So one huge strength of another huge strength of synthetic data is you can actually capture much more diverse imagery than what you'd find on, I don't know, Instagram or Flickr before, where if you train diffusion models on that data, you'll get basically Hollywood actors or models. You're gonna have that inbuilt. Everyone's gonna look great, and humans have a bit more diversity. So synthetic data allows you to sort of capture that diversity, because it's enough to capture a couple of people to represent a particular body shape, and then you can replay that in various settings with various clothing, with various different textures. It's sort of maximizing diversity that way. All right. So once we assembled our digital human, time to create the imagery of it and to create the ground truth. We use Blender cycles, partly because it's open source, it's free, it's easy for us to just spin up 300 nodes to render to something, and also because it's quite easy to instrument. I don't know if anyone's worked with Blender. It has a really nice Python API. You just pip install BPY and you have Blender in Python without ever having to open it, which is great. And it's reasonably amenable to instrumentations. Sometimes you need to hack it around a bit to get specific type of annotation, individual hair strands or certain types of maps, but it's quite doable. Right, so now we have the imagery. We can render a data set of images and time to train our computer vision models. And our training pipelines, nothing special. It's supervised learning, where we have synthetic image in and predicted desired label out. That we play with loss functions and trying to maximize or sort of to minimize the model size, but it's very similar to just training with real data, with one big exception. It's augmentation. So when you're training neural nets with real data, you also use that augmentation. That's a very sort of standard part of the pipeline. However, if you're using synthetic data, you have to use much more aggressive augmentation, because the images coming from your synthetic pipeline are going to be perfect. It's you assume a perfect pinhole camera. There's no lens distortion. There's no ISO noise. There's no compression artifacts from say JPEG artifacts, or you can simulate motion blur. So motion blur you can have, but there's just a lot of things that are there in a real camera, and also not just from the camera. There's going to be a lot of processing things that happen from the capture of the image through the entire camera pipeline, where there's going to be some sort of debayering, sharpening, some now more and more ML retouching of the imagery. So we need to replicate a reasonable amount of that in our augmentation pipeline, and we do it sort of like on the fly. So every image gets augmented differently, but we found that we need to be much more aggressive with our augmentations. Now talking about that. So what can we train with our synthetic data and our model training pipeline? Well, one thing that we've been spending a lot of time training and tuning is landmark models to predict landmarks on a face or full body. And the reason for that is you can use that for tracking faces, reconstructing identity of someone. And typically, people will train 68 or 100 landmarks on the face. Because we use synthetic data, we can train hundreds, thousands of landmarks to sort of increase the fidelity of that. And we can do the same for full bodies. And sort of I'll talk a bit later in the motion capture section of the talk about what we use landmark models for. We can also train models for predicting surface normals on an image, segmenting parts of the face, nose, lips, teeth, things like head tracking. And so, for example, if you use Teams, the background segmentation algorithm, so a half of the training for that is our synthetic data. So you can use it sort of to build production models. And with sort of more recent Surface Copilot Plus PCs, there's a feature that will relight your image to something a bit more aesthetically pleasing. Again, that's trained using synthetic data. And there's a lot of face tracking technology there that's trained using synthetic data. Another sort of thing we did is, I've already sort of alluded to it, is building models that will create an avatar for you. And one of such models that we built is predicting a hairstyle. And from one of the library of our hair grooms. And yeah, hairstyle prediction is really challenging problem. We have a recent paper in SIGGRAPH Asia on that, even just describing what hair is and what types of hair are. That's a challenge in itself. But I think we did quite a good job. And in addition to predicting hairstyle, we can predict the face shape, the eye color, hair color as well, that can then be represented as an avatar in a Teams call. Right, so that's that for parametric models, synthetic data. Let's go into motion tracking part of the talk. And I think I still have 10 minutes. Great. Right, so what do we mean by motion tracking, or just tracking? We use video game terminology in our team, but it's given a video stream or just a single image of a person or multiple video streams, reconstruct what is the parametric body, face, or hand model sort of that can explain that image. And this is just an example of using monocular tracking on different people. Sort of can track full bodies together with high fidelity faces and hands, or just faces individually, and then you'll sort of see hand information. And you can imagine what applications you can build on top of that. For face tracking, you can drive your own avatar. For body tracking, similar story. Or like sometimes we had issues where some of our models that we trained using synthetic data just didn't generalize to certain poses, like someone's crossing their hands or crossing their legs, because there's just very little data like that out there and well annotated. So what we did is let's, in our Capture Studio, let's actually record a person doing this, then use our tooling to register it, maybe do some manual corrections, and now we have that data that we can use in the rest of our pipeline. So that's the virtuous cycle that I mentioned before. So here's another video. So this is from our SIGGRAPH Asia paper from last year on sort of easy to set up motion capture system. And this is just demonstrating it being done using just two mobile phone cameras. No calibration, explicit calibration. The only thing you need to do is time synchronize them. And we just sort of manually sync them. And it's not a live system. It's just for demonstration purposes, an offline system, but just having two video streams, we can reconstruct the person's shape quite accurately without any explicit calibration. It actually calibrates through the detected landmarks. And because our landmark models are just so consistent across views, because they're trained on synthetic data, it works reasonably well. Right, then let me sort of just play that again from here just to see the quality of reconstructions. You can see the finger tracking working well. Then there's going to be an interaction with the face, taking glasses off. That works quite well as well. Right. So how does our motion capture tooling work? Well, we use dense probabilistic landmarks. So for each camera view, or if it's a single view setup, just detect landmarks on the face. Not only the location of them, but also how certain the model is about each landmark. That helps with some self-occlusions or merging information from multiple views when the they disagree about the landmark location. We also, and then we just use optimization, very conventional optimization. We have these landmarks. We have camera calibration. This is our parametric model of the face or a body. Just find the combinations of our parametric model parameters that maximize the likelihood. And it's a sort of a very sort of classical setup. What we do that's a bit less classical is we have an initialization network that will predict the initial parameters of your body, pose, hand shape, face shape, etc. That's just a transformer-based DNN, and then that sort of will be a starting point for your optimization. That really helps with certain unusual poses, with certain self-occlusions or depth ambiguity, and then we sort of just refine that. And one really nice thing with the sort of classical setup of optimization is it copes really well with adding an extra view, adding an extra camera, a camera just zoomed in on the face. We were considering as sort of more end-to-end DNN model that will sort of, just take the imagery and output pose parameter. But that becomes really challenging. But now I can add another camera. Now I remove the camera. Those models are really fragile to that. Optimization-based framework is very, very robust to that. The only sort of restriction we have is it has to be reasonably well time synced, which sometimes is challenging to get. We can do the same with, I already showed multi-view body tracking, but we can do the same with face tracking. So that's where our expression library comes from. And it's sort of like, there's a bit of a chicken and egg problem. For us to get a good expression library, we need to have good synthetic data, but to have good synthetic data, you need to have an expression library. So you do this loop a couple of times with sort of like handcrafted expressions first, and then do better tracking on real data, do some selection of them, and just sort of crank that loop a couple of times till you get something quite good. We can do, monocular full body tracking reasonably well. Some examples of just shape diversity that we can capture as well. And this is an image data set, that's why it's running so crazy fast through it. We can do hand tracking as well, sort of with multiple hands. And one of the use cases for our tracking, in addition to just boosting our entire system, is facial motion capture. So we work with a couple of video game companies in Microsoft where they want to reconstruct their actors' performance. And there are tools out there that solve it, but they're typically very slow in the sense that you capture performance by an actor, send it off to that party company, month, 2 months later, you'll get back the solve. And it's not a very dynamic way of capturing things, and those companies will just actually do a lot of manual touching up to make sure you get a quality solve. And sometimes you don't need that level of quality, or sometimes for secondary characters you're okay with lower quality, or maybe you want a faster turnaround. All right, and with that, I talked about various digital human technologies and how they can be applied for computer vision, not just human consumption, and can build various computer vision models that are already in various products in Microsoft. And with that, thank you very much, and you can find more information here.
Thank you very much, Tadas. Very interesting talk. I think we've got enough time for maybe 1 or 2 questions. So have we got any in the audience?
And I'll be around it for the rest of the day if you want to catch me at the. Sorry.
It's really amazing. I also am a strong believer in synthetic data. So which of these data is available for research purposes?
Yeah. So we released for our. So actually, if you follow these links, so we have a face data set, not with all our dense landmarks, but with sparse landmarks and some segmentation masks. We've released a full body data set for motion capture with simple parameters annotated. And we have a face recognition data set. We've released about 4 data sets out there. They don't have the full end-to-end functionality, but we also got a couple of papers in the pipeline that will also release a bit more, and hopefully even a couple of models that are pre-trained.
So I have another question. Is it so you didn't combine much of real data and synthetic data? Is it because of data sets and data privacy issues that Microsoft is sensitive about, or is it more of a technical decision?
Great question. It's when you start combining real and synthetic, you have now another headache. Okay, how do I combine them? What the proportion of synthetic data should I use versus real? Okay, synthetic data annotations are more accurate, but maybe the data is not more real. You sort of now you have to solve another research problem of mixing that data. So and solvable probably, but if you sort of want to train a normal prediction model, okay, now I have to think, how do I do that with real data? What we sort of instead decided to focus, rather than solving that problem, which a lot of people spend a lot of time looking at it, let's make our synthetic data better to solve that problem. So we look at the failure modes and sort of like, okay, what about our synthetic data isn't that great? You have limited amount of time, and we decided let's invest in that. And so far, I think that was the right choice. And we spent a lot of time looking at, can we appeal this imagery using some like diffusion models or GANs? And then you realize, oh, actually you lose ground truth annotation quality. Then you sort of need to start thinking, okay, how do I appeal it without that? And turns out for a lot of our use cases, you don't need to. It's fine. But yeah, excellent question. It's a question we come back to ourselves. And one thing that we found that's useful, and so, sorry, this is becoming a long answer, training a very heavy model using synthetic data, that will be really big, but because synthetic data still has domain from real data, and then using that really heavy model to annotate some real data. And then you have the annotations on real data, and then you can train a much smaller model on the real data to deploy.
All right, yeah. Thanks again, Tadas. We're out of time for that.